The purpose of this video is to be reviewing oxidation and redox so that you are ready to do the other problems that are in chapter 17 that have to do with batteries. And so you need to remember how oxidation and redox work in order to do that. So again, in this video, we're reviewing redox chemistry. So redox reaction is where something is reduced, gaining electrons, and something is oxidized, losing electrons. This can be determined by looking at the changing oxidation states of the elements. And the oxidation number is equal to the charge of the atom that it would have in the compound if the compound were ionic. So we are looking at oxidation numbers again, which you need to recall for Unit 9 and for the AP Chem exam. And you need to also be able to keep oxidation numbers straight from formal charges. But here, we're not looking at formal charges, we're looking at oxidation numbers. The oxidation number is equal to the charge the atom would have in the compound if the compound were ionic. Consequential to these rules, the sum of the oxidation numbers for all atoms in a molecule is equal to the charge on the molecule. So if the overall charge of the molecule is 0, or the compound or whatever is 0, then the sum of the oxidation numbers must be 0. Even though, as we've talked about at other times, oxidation numbers are somewhat real and somewhat imaginary, just like formal charge. It's a human framework to understand a chemical concept that is sometimes 100% accurate or fairly accurate to what's going on, and sometimes less so accurate. And so these are the rules. You could pause on this slide for a minute to review these of determining oxidation numbers. Hopefully you remember these rules. If not, pause for a second to look at these rules. The one note I will add is that, remember, aqueous ions have charges, but atoms in different states of matter are different than ions. So that means, for example, that if we have aqueous silver, that's an oxidation number of +1. If we have solid silver, that's an oxidation number of 0. So the states of matter really matter. The states of matter really matter. Okay. So here are some practice examples of finding the oxidation number. Go ahead and pause this video if you need to review how to find oxidation numbers, and then we'll go over it. So hopefully you've had a chance to pause this video and go over it to yourself again, how to find oxidation numbers. So here we know that oxygen is almost always -2, except for in hydrogen peroxide. So here oxygen is -2. To make an overall charge of 0, the nitrogen must be +4. Looking at the copper chloride, we know that halogens are almost always -1, and so therefore the metal must be +1. Looking at the next one, again, we know that oxygen is almost always -2, hydrogen is almost always +1. That works out. Going to the next one, we know oxygen is almost always -2, and hydrogen is almost always +1. And so there we have a -8 and a +2. So to cancel out and get a charge of 0, the sulfur must be +6. Going to the next one, H3O+, there is an overall charge. And so to get the overall charge, oxygen's -2. As we know, hydrogens are typically +1. We have 3 times +1 and a -2. That makes +1, so we're good. On the other side, +1, -1. Again, halogens are typically -1. Here we have sodium +1. We know that the first column on the periodic table is typically +1. Next example, again, oxygen is typically -2, hydrogen +1, and so what's left is a cancel out of charge because we have 12 times +1 and 6 times -2, so carbon has to be 0. In the next example, if carbon is -2, then to cancel out and get a charge of 0, or if oxygen is -2, did I say carbon? To cancel out and get 0, the carbon must be +4. The next example, we have an overall charge of -1. We know that, again, oxygen will be -2, and so to get a charge of -1, the nitrogen should be +5. So those are the examples of finding oxidation numbers, okay? Now next, we need to briefly review some examples of determining oxidation numbers in equations, which is basically the same thing. You're just looking at the compounds in equations and looking at the oxidation numbers and seeing if they're changing. So pause and do this one. Okay, hopefully you're able to pause and do this one. By itself, Cl2 is going to be 0, sodium is +1, bromine is -1. Here sodium is +1, chlorine is -1, and bromine is 0. Let's look at the next one. We can see again the oxidation numbers are changing. Cl is going from 0 to -1, and then Br is going from -1 to 0. Let's look at the next example. We have HgCl2. Go ahead and pause this video if you need to. Pause this video, solve it. Okay, hopefully you pause this video, you're able to solve this one. Cl is typically going to be -1. To cancel it out, the mercury is +2. Copper is by itself, so it's 0. So copper is becoming +2 to the chlorine -1 to cancel out the charge, and now mercury is 0. And you should be able to tell me what is oxidized and what is reduced. Go ahead and pause it if you need to tell me what is oxidized and what is reduced. Okay, so mercury is being reduced. It's going from +2 to 0. And then copper is being oxidized. It's going from 0 to +2. Here's another example. Again, pause if you need to. Okay, so hopefully you're able to pause. Sr is 0 by itself. Oxygen is 0 by itself. Now Sr is +2 and oxygen is -2. Another one, pause it. Hopefully you paused. You were able to do it. Again, we have a metal by itself, so it's 0. We have a gas by itself, so it's 0. And now, on the other side, they have charges that would make sense for them being in an ionic compound. Okay, going to the next example, now we need to remember how to complete the half reactions, which we've learned about before. So this is remembering how to add the electrons to half reactions to show where the electrons are moving. Pause this if you need to. Okay, hopefully you paused this and were able to solve this problem. So in the first one, there would be electrons on the right-hand side because iron is losing electrons. And here we'd have electrons on the left-hand side because magnesium is gaining electrons. What's being oxidized? What's being reduced? You should be able to pause and tell me what's being oxidized, what's being reduced. We can say that iron is being oxidized, magnesium here is being reduced. But now we can put these together and consider two half reactions together. So let's look at the next example. This is questions about half reactions. In which half reaction does oxidation occur? And identify the oxidizing and reducing agents and balance the half reactions. So go ahead and pause and try to do that. So in which half reaction does oxidation occur? Li is oxidized. How do we know that? Because it's going from 0 to +1. And then Zn is reduced. As according to part B, I can't recall AP Chem questions asking this, honestly. I feel it's kind of confusing. It's easier to just talk about things being reduced and oxidized than being oxidizing and reducing agents. The analogy I give when I talk about this concept is an assassin or a spy. They are agents. A spy does not spy on themselves. An assassin does not assassinate themselves. They are an agent who assassinates or spies somebody else. And similarly, an oxidizing agent reduces something else. So Li is the reducing agent because it's reducing something else. And then zinc is the oxidizing agent because it's oxidizing something else. Just like a spy does not spy on themselves, something that's reduced is the oxidizing agent because it's oxidizing something else. And then regarding the half reactions, to balance these, hopefully you're able to do that as review. The electrons in each half reaction have to be the same. And sometimes students make the mistake of just writing the amount of atoms that would be in the ionic compound and balancing it that way, right? Sometimes students say, oh, well, it would be a certain amount of atoms if they were to form an ionic compound. In this case, it's two metals, so that doesn't really apply. But you should always balance these based on evening out the number of electrons. So we're just going to add a 2 to the first half reaction. So it's 2 Li, and now we have 2 electrons. So the electrons on each side are canceling. Okay, looking at the next one, skipping this one, going to the next one, see if you can write these half reactions and then balance them, again, based on number of electrons. Go ahead and pause it if you need to. Try that. Okay, hopefully you've had a chance to pause it if you need to and try that. So, for our two half reactions, we have Al, and this is becoming Al3 plus 3 electrons. I'll note that in AP Chem, in this example problem, they didn't give us phases. If they give you a phase, I would write it down. So like if they tell you, or it's implied this is solid, and that the aluminum here as the ion is aqueous, I would definitely write that down because they definitely can check for that in terms of your grade. And then the other half reaction, we'd have H plus 2 electrons makes H2. Now, we can't just write H plus electron makes H2 because then there's 2 hydrogen atoms on the right and only 1 hydrogen atom on the left. So that doesn't make sense. So that's why I originally wrote it as 2H plus. And again, if this was like AP Chem and they implied what the phase would be, you should include those. So if we were balancing the overall half reaction, then we need to make sure the same number of electrons are on each side. And so in this first equation, we're going to have to get to 6 because that's the least common multiple of these two. So I'm going to double it. So we have 2Al making 2Al3 plus 6 electrons. And then the second one, 6H plus 6 electrons, making 3H2. And now the electrons are balanced in the two half reactions. Let's look at another couple examples in case you need them. So pause if you need to, and then we'll go over it. Okay, so hopefully you paused if you needed to. So Cu is going to make Cu2 plus 2 electrons because it's losing 2 electrons. And then Ag plus is taking in an electron to become Ag. And then we can balance these to make sure that the same amount of electrons are on each side. So we're going to double this second equation here. Let's look at the next one. Pause if you need to in order to solve it. Hopefully you're able to pause. Okay, so now we have Li, and Li is becoming Li plus and losing an electron, and we have nickel, Ni2 plus, and that is taking in 2 electrons to become Ni. And again, if it was an AP Chem problem where they implied what the phases would be, you should write them. So when you see like the mock MCQ practice problems and mock FRQ practice problems, they'll probably imply phases or make it clear what the phases would be. And so this first practice problem should, or this first half reaction should be doubled so the amount of electrons are the same on each side. Let's look at one last problem. Again, pause if you need to before going over this. Okay, so we should have Cr becomes Cr3 plus 3 electrons. And then the second one would be Ag plus an electron becomes Ag. But again, there's only one electron in that second problem. So we're going to triple it so the number of electrons in each half reaction balance out. Now, in terms of AP Chem, they make specific note that problems where you add H plus, add acid, or add OH minus are out of scope. There's some OpenStax questions that have that. Perhaps, undoubtedly, if you Google oxidation half reaction, redox half reaction practice, you could see problems that require adding acid or base or require an acidic or basic solution. That is outside the scope now, at least, of AP Chem. That is not the focus. So the most complicated half reactions you need to be able to write and understand are the type that we already just went over. If you know how to do those more complicated problems, great. I kind of like it that you might get some brief exposure to it. I think I assign a couple in the reading guides just so if you've seen it before, because there's a decent chance if you were to take general chemistry in college, they would expect you to know how to do those first semester. So at least you've seen them, but I'm not going to harp on them because they are not harped on or focused on for the AP Chem exam. So that is it for the oxidation review, and that gives us the review we need in order to learn new material in Chapter 17 and finish AP Chem. Yay! All right, so hopefully that was good review for you.